This is the fourth video on ideal gases, where I am looking at the kinetic theory of gases, and the learning outcomes are as follows. You should be able to state the basic assumptions of the kinetic theory of gases, explain how molecular movement causes the pressure exerted by a gas, derive and use the relationship PV is equal to 1/3 nm times the mean square speed. We are considering the simple model in 1 dimension and then the complex model as well in 3 dimensions. Understand that the root mean square speed is given by the square root of the mean square speed. Compare PV is equal to 1/3 times the mean square speed to PV is equal to nkt to deduce that the average translational kinetic energy of a molecule is 3/2 kT. Consider subscribing to the Physics Tips for Cambridge Students YouTube channel. Hit the bell notification so that you get alerted of my future videos. Without much further ado, please let's get started. In the kinetic theory of gases, Brownian motion and diffusion were stated as the ones providing evidence to the existence of this theory. And according to the theory, matter is made up of randomly moving particles. They could be molecules, they could be atoms. The theory relates the macroscopic behavior of an ideal gas with the microscopic properties of its molecules to obtain expressions for the pressure and temperature in terms of the speed, number, and mass of the molecules. Now we're going to look at the relationship between molecular speed and the pressure. The assumptions that we're going to be making here, the forces of attraction or repulsion between the molecules are negligible except during collisions. The duration of a collision is negligible compared with the time interval between the collisions. The volume of the molecules is negligible compared with the total volume occupied by the gas. The collisions between molecules and their container walls are perfectly elastic, and also that there are many identical molecules that move at random. So these assumptions effectively describe an ideal gas. We're going to start the derivation. Consider a gas molecule of mass m in a cubic box of side L. So that's L times L times L. And then the molecule is moving at a speed c, which is parallel to the base of the box towards the right hand side. Now the change in the momentum of the molecule when it collides with the wall, the reason why we want to find the change in momentum is we want to know the force. Remember, pressure is equal to force over area, so the rate of change of momentum is force. If you find the momentum change and divide by the time taken, we can find the force. So change in momentum is equal to final momentum minus initial momentum, which is minus mc, taking vectors to the right as positive, left as negative. So final momentum is to the left, initial momentum is to the right. So minus mc giving you minus 2mc. This molecule travels a total distance of 2L because it's going to move from left to right and then from right to left. So that's going to be 2L. And then to find the time is going to be distance over the speed. So that's going to be 2L over c. The rate of change of momentum, like I said before, is equal to the force. So we're going to say the momentum change over the time, minus 2mc over 2L over c. We have dropped the minus sign because we're just going to consider the magnitude of the force. So it's going to be 2mc over 2L over c. Then that gives you mc squared over L. The area of the wall is L squared. Force over area is the pressure. So this is the force mc squared over L, and the area is L squared. So this divided by L squared, that's going to be mc squared over L cubed. Now in practice, a typical molecule moves randomly and collides with all 6 faces. So we have just considered for one face here. It's going to consider the other 3 faces. So we can multiply by the 3 times. That is for all the 3 faces. So the total area involved is going to be 3 times that which you've considered. Pressure will be equal to mc squared over 3L cubed. Now the total number of molecules is n, because here we've just considered for one molecule. So if n molecules would make it change to n mc squared over 3L cubed. And also we know that each of these molecules is moving at speeds that vary from C1, C2, C3. So depending on the number of molecules. So it's C1 squared plus C2 squared plus C3 squared all the way to Cn, that's molecule number n. You square that, you divide that by n to get the mean square speed. The mean square speed is literally the sum of all the squared speeds of the molecules divided by the number of molecules, which is n. Removing n from the denominator, you have nc squared, will give the sum of all the mean square speeds. Now the total pressure exerted now is going to be equal to the force over the area, and the force we had hit here as mc squared, now it's going to be nmc squared over the three faces, which is 3l cubed. So the volume of the box is L cubed, so that's volume is V. So in place of L cubed, I'm now going to put a V over there. So I'm going to get it as 1/3 Nm over V C squared. Then taking V the other side, it's going to be PV is equal to 1/3 Nm C squared. This is known as the kinetic theory of gas equation. P is the pressure of the gas, which can be measured. Volume is the volume of the gas, which can be measured. But then on the right hand side, we're going to get the microscopic, which cannot be measured. So the number of molecules, and then the mass of one of the molecules, and then the speed, mean square speed of the molecules. So the left hand side macroscopic, the right hand side microscopic. Since Nm is equal to the total mass of the molecules, and V is equal to the volume, we can find the density of the gas by saying Nm over V. So taking V down there, it's going to give you Nm over V is equal to the density of the gas. So P is equal to 1/3 rho C squared, where rho is the density. Right, so I'm going to do an example here to show you how to work with mean square speed and the root mean square speed of the molecules. Says here that the table shows the distribution of speed of 20 particles. So we have the speeds and then the number of particles with that particular speed. The first particle has a speed of 10 meters per second. Second particle, there are 3 particles there with speed 20 meters per second. So the first one says, what is the most probable speed? So in finding the most probable speed, we are just finding the mode. That is the one that has the greatest frequency. The speed with the highest number of particles here, 8 particles, would be the 30 meters per second. Hence we see the 30 on the answers there. And then the average speed, we need to find the total speed, right? So for that would be 1 times 10 plus 3 times 20 plus 8 times 30 plus 5 times 40 plus 2 times 50 plus 1 times 60. Just put a 60 there. And then divide by the total number of molecules. That is going to be 20. So if you do the maths there, you're just going to get the answer 33.5, which is just around to 34 meters per second. Now to move on to the mean square speed. Remember I said that this is equal to the mean of all the squared speeds, or mean of the square speeds. In place of this, I'm going to put that squared over there, and then this will be squared, this will be squared, this will be squared, this will be squared. So I'm looking at all the squared speeds. If I do that and then divide by 20, you're going to get 1255. So please do it and then let me know in the comment section. Then to find the root mean square speed, the root mean square speed is going to be equal to the square root of all these square speeds. The square root of the mean square speed gives you the root mean square. And if you do that, you're going to get about 34.8. That's rounded up to 35 meters per second. In the second example, we are asked to calculate the root mean square speed of air molecules in a container in which the pressure is this and the density of air is that. So what we're just going to do there is to apply the equation P is equal to 1/3 rho, then the mean square speeds, like that. So we are given the pressure. So we first of all find the mean square speed, which is going to be equal to 1.0 times 10 to the power of 5 pascals over the density 1.3 times the 3 there. after you've done that, since they want you to find the root mean square, remember I said that the root mean square speed is equal to the square root of the mean square speed. So the square root of that would give you the root mean square, the RMS speed. So if you do the maths, you find that you get 480 meters per second. Right, so I'm going to end the video right here, and then I'll look at temperature and the kinetic theory in the last video. Signing out.